If f of z is an analytic function that maps the entire finite complex plane into the real axis, then the imaginary axis must be mapped onto the entire real axis, a point, a ray, an open finite interval, or the empty set. Well, it can't be the empty set, right? F of z is an analytic function, maps the entire complex plane into the real axis. The imaginary axis must be mapped onto Is this even, I'm a little bit confused here. F is an analytic function, maps the entire complex plane into the real axis. Then the imaginary axis must be mapped onto something. My first instinct here is that it's a point, because if F is analytic, my complex analysis has been dormant for a very long time, but this means that F is holomorphic, right? And so the function is nice around a ball, and so it has to map a ball into some kind of set, which is not totally trivial, unless the function's a constant. It can't map the imaginary axis. Oh yeah, so this is the thing is that the function is real everywhere, right? So the entire complex plane is mapped onto the real axis. There aren't holomorphic functions that do that other than constants, right? Think, for example, of a polynomial. If f is a polynomial does not map into only the reals. I don't have a proof or anything, but I think the answer is just B, a point. I don't really know how to properly explain my thoughts in a very clear way, but suppose the function is not a constant. Okay, then f is analytic. I'm 99% sure this means it has a well-defined complex derivative. If I take any point in the imaginary on the imaginary axis, and I assume the derivative of that point is not 0, then by moving, let's say the derivative of this point is real. If the derivative of that point is real, then when I map it to the real axis, if I move in the imaginary direction, the derivative will move me in the imaginary direction, which is a contradiction, because we have to stay on the real axis. Yeah, I think we have to have f prime as 0. I'm sure there's a theorem in functions of complex variables that say that complex analytic functions map. Do they map open sets to open sets or something like that? Or except for constants? And I think that's kind of the idea, right? If the derivative at a point is non-zero, then by moving in any direction that I want away from that point, the image can also be made to move any direction we want away from that point. It'll be rotated by the direction will be rotated by the, what do you call it? The angle of the derivative, the argument. I don't remember any of my complex analysis terminology here, but yeah, I think the answer's got to be a point. I'm going to, for most of these questions on this GRE test, I haven't actually checked whether my answer is correct or not with a very small number of cases. This one I really do need to check whether I'm correct. So I'm just going to do it right now. Let's see if the answer is B, a point. Yes, it is. It is a point, B. Okay. I'm happy. I used to be really good at complex analysis, but this is the first time I've even thought about it in well over 10 years. So that's cool. Yeah, there's a lot of intuition that can be built over around functions that are holomorphic. And you know, if you have a holomorphic function, you're never going to see like the image of something being. Holomorphic functions map nice things to nice things, basically. Yeah, I suppose holomorphic functions map nice things to nice things. And so if it maps the entire complex plane onto the real axis, that sort of made me think that there's something wrong with this function. And the thing that's wrong with it is that it's a constant. So if it's constant, then in fact maps everything to a point. That's it. It was kind of like an intuition that kicked in at some point. But it's further expanded by this argument about how with a holomorphic function, you can move the image of a point in any direction you want by moving the original point in some direction. So you, as long as the derivative is non-zero. But again, if we're a constant, the derivative is zero anyway. Yeah, if I have more to say, I'll put it down in the description. Sorry for rambling. Thanks for watching.